Hey guys, welcome back. Day 29. And we're talking about chemical reactions today. Finally, 29 days in to talk about chemical reactions, but here we are. The first thing we're going to talk about, right, is a reaction and then what evidences a chemical reaction has. So we know reactants, we start with reactants. Reactants react and they make products. All right. What are the evidences that this is happening? All right. And so some of the evidences, like one of the first one, it's on fire, right? So you think fire, right? Which is basically heat and or light produced. Right? That's the first one. Heat or light produced. All right? Another one. All right? Another one that happens, rust would be an example, right? Which is a permanent color change. Right? So if you have a bicycle and your bicycle went from like that dark gray or a even light gray, and now it's starting to become orange, that's a permanent change. It's a permanent color change. You can take the rust off, but that iron reacted, right? So your bike chain is actually a little lighter. Two more. And we call this one precipitation, which is the formation of an insoluble solid product. Right? So if you had a test tube, the bottom of a test tube here, right? And you had some type of, liquid in there, right? You're not going to get, oh, that's an arrow. Sometimes the shapes are great, sometimes they're not. You're not going to get that in the bottom of the test tube, right? What actually happens is that you get this, it looks like lots and lots and lots of dots coming down, and they precipitate down to the bottom to end up with something, eventually that will look like sand in the bottom of the beaker, the bottom of the test tube, right? So if you go to the beach, I happen to live near the beach, right, not too far, within a half-hour drive. You go to the beach, you skip up some beach, water. It's got all sorts of stuff into it, right? But as you let it sit there, that all the stuff in the water, all the solids, go to the bottom of the bucket, and the top is clear and colorless. It still has the salt water and stuff in it, but it's clear and colorless, right? So that's a precipitate, when you mix two things and you make a solid. And last but not least, right, gas formation, right? Which is, we're just going to put gas formation, right? Sometimes you notice in the fridge, you can smell like a gas was formed. You know something is bad, right? Those are your evidences of a chemical reaction, right? Heat or light, permanent color change, precipitation, which is a solid, or gas formation. Now, reactants to products, we need information about the reactants and products and sometimes the conditions to help us know what's going on. So as you probably see, these down here are state symbols. And you have solid, liquid, gas, and AQ. Aqueous, right? That means it is in water. In water, right? So it's not, right? If something dissolves, dissolving is a physical change. So if you put salt in either the ionic compounds in water, you put sugar in water, it becomes aqueous, right? It's in water. It's still sugar, it's still salt, but it's in water. This triangle, right? That means heat is required. That means platinum is a catalyst. That's the actual temperature required, right? The solvent, so let's say you had methanol or dichloromethane. DMSO, there's there's tetrahydrofuran. There's lots of different solvents besides water. All right, okay, and so that all that, so those, so we know. I can draw a line here. We'll use this color. These on the left, the state symbols go in reactants and products. So you know the state that is being made and used. All right. Everything else goes with the arrow on the right hand side there. Now there are 5 classes. We're going to talk about actually 6 reactions. Combination or synthesis. So combination or synthesis where you have 2 things, A plus B, going together, AB. Classic example, right? H2 with a gas plus O2 as a gas, and that's going to make H2O as a liquid. Why a liquid? Well, because technically we're going to be at 25 degrees Celsius in chemistry land here. And so 2, 1, 2. We're going to learn to balance that soon. Decomposition is the opposite. All right. Okay, for example, a good decomposition reaction would be NaHCO3 solid. We add this, right? That's baking soda, right? And that makes Na2CO3, sodium carbonate, plus carbon dioxide gas and H2O liquid. And to balance that, you just need a 2 there. Right? Baking soda is a great example. Single replacement. Some books call it single displacement. So you have AX plus B going to A plus BX. Right? So for example, Cu. Let's use green. SO4 plus magnesium goes to Cu solid plus Mg SO4. So when you look at that, it looks like sulfate would rather be with magnesium. That's really not what happens. Okay? You'll learn later on, really just basically electrons on magnesium would rather go to copper. But it looks like single replacement. I like to call it like junior high dating. When I was, a kid in middle school, even early high school, people could not drive, right? Hopefully. And so they would hold hands in the hallway. It was the big dating thing back when I was years ago. And whose hand you were holding, I guess, was important. I never held anybody's hand because I didn't really care. But call it, junior high dating. Or, copper's available now. Oh, no, magnesium's available. I think it's fun. A lot of people remember it that way. Anyway, double replacement. This is a very common reaction, and it's switch and dance partners. All right, so you have AX and BY going to AY and BX. Extremely common reaction, and a classic one, silver nitrate plus sodium chloride. We get silver chloride and sodium nitrate. All right, we're going to stop there for a second. And I'm going to point out the evidences of chemical reactions. So in the first one, right, This is this is a combustion as well, right? That's number 6. And so you're going to have heat and light produced for the first one. For the second one, you have the gas formation. For the third one, you actually have a color change. You make copper, right? Magnesium looks like a certain silver metal, and copper looks like copper. All right. Plus, copper 2 sulfate in solution is blue, and magnesium sulfate in solution is colorless. Here, you make a solid for the double replacement. The last one is neutralization, where you have an acid plus a base goes to a salt, which is any ionic compound, plus water. And when you do this, there is no evidence of a chemical reaction. Right? What do I mean? The acid, HBr, plus the base. Okay, I'll use pink here. I'll use OH. And the salt would be potassium bromide. And then, of course, you get water. And so, hydrobromic acid, especially in a dilute solution, does not look any different than water. Potassium hydroxide doesn't look any different than water, right? Potassium bromide in water looks just like salt water. So there's no evidence of chemical change. Don't get me wrong, there's definitely differences here, right? You would not want to swim in potassium and hydrobromic acid. You won't want to swim in potassium hydroxide. A little bit of potassium bromide in water, not a problem. Okay, it's not gonna burn like the other ones would. So that's why I have it as its own class of reaction. And then number 6 here is combustion, and that's a reaction with oxygen. Right, so every time you see O2, like there, that's a combustion reaction. So methane plus oxygen gas goes to carbon dioxide. So almost always products of combustion, right? And to balance it, we need a 2 there and a 2 there. But if you look, your products of combustion are going to be whatever nonmetals there is there, and usually water, right? That's usually your product, because if you have a nitrogen compound or a sulfur compound, you're not going to make carbon dioxide, you're going to make sulfur dioxide or nitrogen dioxide, okay? But that's your basics. So that's your 5 classes. And the reason we do that is it's going to help you understand the class, and then that leads us to balancing, right? Balancing chemical reactions. That's very important, right? Because the chemical equation represents the chemical reaction, right? And we know a reaction is a rearrangement of the same set of atoms. Bonds are broken and new bonds are formed. Coefficients in the equation describe the stoichiometry, which is the moles of reactants required and the moles of product formed, right? And so the mole ratio, the particle ratio, is how we measure these reactions. Not how we measure it, how they react. We measure the reactions not with moles, we measure it in mass right now. We'll get to some other ones soon, but right now we're doing mass. We measure in mass, but the reactions react in moles. And so we need to know the particle ratio, which is the mole ratio. We use mass ratio, the molar mass, to get from a mass to a mole, and then the mole ratio is how they do it, right? And so, for example, It's 2 here. Now, there is a 1 in front of H2 or O2. We don't write it in a 2. And so, if I was going to make this reaction happen, I need 2 moles of hydrogen for every 1 mole of oxygen. Now, that's not a mass ratio. I don't need 2 grams per 1 gram. That's not the mass. It's the moles. It's the particle ratio. Right? And so, that's the coefficients. So, how do we balance them? What is the way to balance these? The first way to balance the equation, and this is very, very important, okay? Right? This is done not because it's like a system, it's by inspection. So since it's by inspection, I'm going to say use pencil or like what I'm, a screen that you can erase on easily, because erasing will happen. It just will happen. You're not going to do anything wrong. You're not making mistakes, but it's going to happen. All right? The first and the hard, it's in red here. That is the hardest part right there of all balancing equations, is writing out the correct chemical formula. Because it's not always going to be given to you you're not going to always get chemical formulas. You're going to get words. Copper 2 nitrate reacts with magnesium to make copper metal and magnesium nitrate, and you'll have to write the balance equation, so you have to make the formulas first. Then when you balance, you select the most complicated formula, the nastiest one, the one with the most elements in it. All right? And in that nasty formula, you start with the atoms that only occur in one compound on each side. So you take the biggest, nastiest one, right? And then you use that, whatever elements only occur in one other compound on each side, that's what you use to balance first. All right? Then you leave simple molecules and atoms like H2 and O2 until the end, or Fe or Mg, right? Because then if you only put a number in front of Mg, it doesn't affect any other element. And then another thing that's fun is polyatomic ions that do not break down, and they exist on both sides. They can be treated as a unit. So you can balance phosphates or nitrates or sulfates as long as none of them break down. All right. Now, how do we get better at this? By practice. So here are 3 examples that we'll do. All right. So I have aluminum carbide and water, aluminum hydroxide, and methane. Which one's the worst? I would start with either this one or this one. All right? Typically, we leave O's and H's to the end. Leave O's and H's to the end. That's my recommendation. All right? I would H last, O second last. And sometimes you do H and then O last. So it just depends. I leave those 2 elements to the end. So if we look at aluminum here, I have 4 aluminums. Now, can I just put a little 4 right there? What do you think? Well, the answer would be no, right? That's not allowed. And we can't do that, right? Because that would change the compound. I can, however, put a 4 right there. So now I have 4 aluminums on both sides. Carbon. We have 3 carbons on the left, 3 carbons now on the right. So now I have 4 aluminums here and 4 aluminums there. I have 3 carbons there, 3 carbons there. Now, if I look, I'm going to pick oxygen. And so I have 1 oxygen here, okay, but I have 3 and 4, right? You see how, so this 3 is in the parentheses, so there's 3 hydroxides. It's OH, OH, and OH, right? So there are 3 of them, but there are 4 aluminum hydroxides. So I take the 4 times the 3, so there's technically 12 oxygens here. That's a 0, 12 oxygens. Right? And so I would need to put, right here, I would need to put actually a 12. Wow. All right. So now how's hydrogen look? Here I have 24. Here I have 4 times 3 is 12, and then I have 3 times 4 is 12. And so 24 does equal 12 plus 12. It works out. So you can always balance these, and you can always double check them. 4 aluminums, 3 carbons, 24 hydrogens, 12 and 12, 24 hydrogens, and then 12 oxygens, 12 oxygens. Okay. Next one. Well, I would start with ammonia. Start with the nitrogen. It's good. Excellent. Hydrogen. I got 3 here, and I have 2 there. Well, I got to make it the same. Well, 3 and 2, the lowest common multiple would be 6, wouldn't it? So that means I put a 2 here and a 3 there. So now I have 6 hydrogens and 6 hydrogens. But what do we do with nitrogen here? 2 and now 1. So I have to go back and put a 2 there. Oxygen. So right now we have 2 here. On the right side I have 2 plus 3, so that's 5. Ooh, what times 2 is 5? 5 halves, of course, all right? We don't like that though, do we? I don't like that. So how would I get rid of the 2? You have to double everything. So I have to make this 2 a 4, and then the other 2 a 4, and the 3 a 6. So I had to erase every coefficient but 1 to do this. Now, what do we need to do? We need to double check this. 4 nitrogen, check. 4 times 3 is 12 hydrogens. 6 times 2 is 12 hydrogens, check. 10 oxygens, 4 and 6, 10 oxygens. Perfect. Lastly, propane. So we got propane here. I got 3 carbons on the left, so I need to put a 3 in front of CO2. And then we got 8 hydrogens on the left, 2 on the right now. Put a 4. So now we have 8. And now we gotta look at, so I got 3 carbon, good. 8 hydrogens, good. I have 3 times 2 is 6, and 4, so that's 10. So that means, divide that by 2, we have 5. 5 oxygens again. So that is balancing. Now next, in the next video, just to be consistent, we're going to talk about some reactions with more reactions, like type of reactions with different groups of the elements, all right? And then after that, we will do some examples of why we balance it, and then lots of examples and examples and examples. All right, hopefully this makes sense. Again, we're going to do some more videos with balancing, all right? So go ahead and watch those. If you have any questions, feel free to reach out to me. And until then, we'll see you next time, guys. Take care.